Hello, my name is Lillian Chin, and I'm here to present about flipper-style locomotion through strong expanding modular robots. So modular robots have been able to show great resilience and robustness by having multiple modules work together and having their local behaviors create global emergent properties. There are two main architectures that most modular robots fall under. One is this chain architecture, where you connect individual modules into a line, and the other is this lattice architecture, where you can have individual modules linking up together to form a lattice. These have been shown to have great applications in modular robotics, but one of the big issues is that any sort of global shape change requires physical movement of as many modules. This is working great for these s'mores modules, as you can see moving around here, but as the number of modules increases, shape change becomes harder because you need more modules to move around. One way to get around this problem is through volume changing. So in this image, you can see that these individual particles, which can't operate well on their own, can expand their size. And in doing so, they're able to move together as a swarm and perform light following. So this shows that volume changing is an exciting way that we can use modular robots to get this global shape change without having to move individual units. This idea of volume changing has its basis in biology as well, as you can see through this plant movement, where the increased growth of cells on one side enables the plant to do light following itself. However, when we try to make volume changing robots in the lab, we soon run into difficulties. One, for example, is this older work about the telecubes, which uses lead screws to actuate each of the individual faces of the cubes outwards. Although it was quite effective, it was difficult to build off of due to its complex actuation. Recently with soft robotics, we've been seeing a lot of excitement of volume changing through inflation, especially through soft systems, but then this has its own difficulties with the system having to be tethered to an external air supply. So in this work, we seek to address these concerns by introducing auxbots. They are an untethered motorized auxetic shell, and through the geometry of how we configure it, it is able to have a large expansion and large force output. The main way that we're able to achieve this is through the geometry of the structure itself. Buckminster Fuller, better known for the buckyballs, invented this structure called the jitterbug, and as you can see, these individual polygons rotate against each other. This math is very well described, but it basically is nice because it links the rotation of these polygons against one another to an overall expansion of the structure. So, if we can create a system that maintains this angular constraint between individual polygons and have it expand outwards, we can then have an entire individually controlled system that can expand its volume. Because it's so modeled mathematically, we can have both volume models of how the system will move as well as individual face movement, which matches very well. Mechanically, how this works is that aside from the external auxetic shell, we have this internal actuation module. It's powered from a lead screw, which expands at different sizes and forces the polygons to rotate against each other. And we have this 3D printed angle constraint to ensure that we have a good match with the mathematics. When we do mechanical testing of this structure on the Instron, looking at both the system axially, so along the length of the lead screw, as well as laterally, perpendicular to the lead screw, we see that we have a very high amounts of force. With the axial direction being able to exert more force outwards. Specifically, we're able to achieve a maximum expansion force of nearly 76 times the weight of the individual actuator and 40 times the weight of the individual module. This is exciting because it means that we have a system that can independently control its volume and push out with this very strong force. We can use this high force to our advantage by attaching a cable constraint between individual auxbots. As you can see in the bottom picture, by tying this cable constraint against one another, we're able to create this bending motion across an auxbot system as each of the modules expand. Then, by putting different modules together, each of the cable constraints is providing not only a bend, but a slight lift, which enables the system to move forward. We believe that this is the first time that flipper-style locomotion has been able to be achieved through modular robots. With this style of locomotion, we're able to achieve new functionalities such as heavy hauling of weights. So in this example, you can see we have a quadruped sort of sea turtle-like design, and it is able to haul 1.5 times its own weight, even when the back motors are stalling out due to the weight, too much force being put onto the back auxbots. This is thus achieving the dream of resiliency and robustness that modular robots so desire. If we compare this to comparable work of other modular robots, we see that the Oxbots are nearly 10 times faster than other forms of modular locomotion. We're able to achieve this because the high force output is significant and is able to not only go against the amount of friction on the ground, but push the rest of the Oxbots forwards. We also note that while the Oxbots do not have the highest expansion ratio and speed, they are comparable. In this literature review, we saw that the Oxbots were the second highest in terms of strength to weight ratio and had a decent amount of expansion ratio to compare. So with that, I would like to thank my collaborators, and I encourage you to come visit me at ICRA for more information. Thank you.